Hi everybody, welcome back to the Feynman technique. This is going to be a three-part video in preparation for solving that integral with Feynman integration. I got that integral, as I often do, off the channel Maths 505. He solved it with contour integration. I will, of course, be solving it with Feynman integration. The first part, I decided to break this up into three separate videos because there's actually there's three cool things that are shown in it, and I wanted to make sure that all three of them were highlighted. The first two parts are not going to have any Feynman integration in them. The first part is just proving or showing this identity, that arctangent x is equal to I over 2 times the natural log of x plus I over x minus I plus pi over 2. That plus pi over 2 is actually important. I've seen this identity on the internet a whole lot, and for some reason, some people forget that plus pi over 2, but that actually should be there. And here's what we do. We all know this. We all know that arc tangent x can be represented this way as the integral going from 0 to x of 1 over t squared plus 1 dt. And now this indefinite integral evaluates to arctangent t. Plugging in x, we get arctangent x, and then minus arctangent 0, which will be exactly arctangent x. But this can also be written like this. This can be the integral from 0 to x of 1 over t plus I times t minus I dt. You can see this will be t squared minus it plus it minus I squared, or just plus 1, which will just give you this. So now we can use partial fraction decomposition on this integrand right here. So doing that, we would have a over t plus I plus b over t minus I equals 1 over t plus I t minus I. And then cross multiplying on this, you know how it goes. You know how partial fraction decomposition works. I don't even need to really do this part, but I'm going to. Let's see, this would mean a t minus I a plus b t plus I b is equal to 1 plus, of course, 0 times t. Now we match up our t terms and we'll get a t plus bt is equal to 0. In other words, a plus b is equal to 0. In other words, a is equal to negative b. And what do we get if we match up our constant terms? We get ib minus ia is equal to 1. So let's write that down. ib minus ia is equal to 1. Dividing both sides by I will give us negative I on the right. Now, we have a is equal to negative b, so I'll just switch this to a plus b, or just 2b is equal to negative I, or b is equal to negative I over 2, and therefore a is equal to I over 2. Now we can replace this on we can replace a and b with I over 2 and negative I over 2 respectively. so there's the partial fraction decomposition on this. So I'm going to erase this part too. Well, if this is equal to this, then let's just integrate from 0 to x dx. And that should be the same thing as this, which is the same thing as this, which is the same thing as this. So what are we going to get? Well, first of all, of course, we'll factor out an I over 2. And then we'd just be left with the integral of 1 over t plus I minus 1 over t minus I. And that is going to give us the natural log of t plus I over t minus I. And then, of course, we would have to evaluate this from 0 to x. Okay. So now, finally, what do we have? Well, we're definitely going to have this I over 2. And then we will have a natural log of, let's see, plugging in our upper bound, we have x plus I over x minus I. And then subtracting our 0 bound, we have I over 2 times the natural log of, let's see, 0 plus I over 0 minus I, or just negative 1. Okay. What is the natural log of negative 1? Well, we know from Euler's formula that that can be expressed as e to the I pi. That is, negative 1 is equivalent to e to the I pi. Using the properties of logarithms, this simply becomes I pi. Times I pi. This I and this I combine to make this a positive. Then we have pi times 1 over 2, or simply pi over 2, and we're done. Plus pi over 2. So this identity that the arctangent of x is equal to this thing right here will be used in part 2 of the video, that is in preparation for solving this integral with Feynman integration. All right, well, I hope you enjoyed that, and we'll see it in part 2.